Okay, so welcome to Math 383 Complex Analysis. This is lecture 20. What I want to do today is continue talking and actually finishing our discussion on zeros of functions, a little bit on Weierstrass products, probably talk a little bit about conformal maps. And again, what I want to try to do is adjust a little bit of what material we cover in class versus what material you cover at home. And again, as you go into graduate school, there's just not time to cover everything you need in lectures. And so lectures become extremely tailored. You are encouraged to work in small groups and whatnot. As you're doing the reading, as you're listening to the videos, if there are specific things that you would love to have discussed in greater detail in class, let me know. Otherwise, I'm going to try to adjust based on the expressions I see on your face and the comments I see on homeworks and exams in terms of what to do. As a default, more real analysis, more analysis review seems to be a good allocation of time. And unless I see otherwise, I'm going to do that because once you have that mastered, you can then apply that to a whole slew of things. A lot of these proofs are extremely similar. It's the baby is crying. And so when the baby is crying, you just start going through the list of all the different possibilities as to why is the baby crying. And after a while, you get a better sense of which thing it could be. A lot of the things are very similar. We proved Rouchet, and after we proved Rouchet, what did we get? Anybody remember what came after Rouchet? I'm sorry? No, argument principle led us to Rouchet. It was argument principle, then Rouchet, then open mapping, and after open mapping was Max-Moduli. So we've got that whole chain. Rouchet was really the thing that started it going, and that was really the argument principle. And it's just trying to find a good, convenient way to use that. So we talked a little bit about products, infinite products. When does it converge? And if it's going to converge, we need the terms to be tending to zero. So typically what that means is, well, at some point, yes. Oh, thank you. So let me try to get people back into the Zoom. Thank you. And so I'm going to upgrade everybody who is in Zoom land right now to a co-host. If you see somebody whose name is not going to bomb you or something like that, please let them in. Thank you. Okay, so that should hopefully be everybody. Okay. So if a product is converging, we want the terms an to be tending to 0, which means that the individual terms in the product are tending to 1. And so frequently we'll say, look, if the terms are tending to 0, then eventually all have to be less than 1/2 an absolute value. So if you think about what's going on, if this is the complex plane, and this is IY, and this is the x-axis, here's the point 1. Eventually, I've got to have some small ball about 1 where all the 1 plus ANs live inside here. So I can define a logarithm. So define a logarithm, use for all n sufficiently large. So there could be a couple of terms. Maybe the first term, an, is going to be -5. Screw it. Just remove finitely many terms in the beginning. And then from that point onward, then you look and see what's going on. So eventually, all the terms are going to be close to 1, so I can use a nice branch of the logarithm. And so if I want to study what's going on, we have a Pavlovian response. Whenever I see a product, the log of the product of 1 plus an, n goes from 1 to infinity, is the same as the sum, n goes from 1 to infinity, of the log of 1 plus an. And then by my Taylor series, this is going to be the sum, n goes from 1 to infinity of an, minus the sum, and it goes from 1 to infinity of an squared over 2 plus ... Right? Now, as soon as I do this, I've got to be extremely careful because I've got each logarithm, I'm expanding, and then I have a sum over n, and I'm breaking things up. The reason I can do all of this is all of this stuff here is small. Okay? Why is it small? Well, the ANs are going to be less than 1/2 an absolute value. So for each one of these, I'm going to have a geometric series. And they're going to be getting smaller and smaller and smaller. And so I want to say that when I combine all of them, it's going to be okay. So it's a really nice exercise. Write this up rigorously. And I'm happy to take a look at it. So how would you rigorously write up that we could do this? So, one of the things you could do is you can say, look, the log of 1 plus an, let's see, I'll assume for now, maybe an is greater than 0, just to be simple. That's going to be an plus, the sum, k goes from 2 to infinity of -1 to the k plus 1, an to the k over k. And I want to just get a sense of how big could that be, right? It can't be too large. And it's got to be such that, when I combine it with the ANs, it's still going to be of a comparable magnitude. And so what we end up getting is the key result is the product converges if and only if the sum of the ANs converge. So the ANs converge and the product converges and vice versa. If you go back to the examples we did before, and I think this is the nice thing about doing the slides like this, is I should be able to pull up what we did, if I can find the right day. Is this today now? Okay, so here's a bit further. We had some of these products. Is it maybe the last one? I thought we had some products. Okay, here's the products. Here we go. So if we look at these products, the sum of 1 over n, that diverges. And so we would expect that product to diverge, and it actually does diverge. It diverges to infinity. The sum of 1 over n squared, that converges. We would expect the product to converge. It does. So the intuition we might have been grasping by looking at this special case actually holds. And of course, the intermediate one, the 1 over n squared minus 1, well, as a nice exercise, show that that is the same as essentially the same arguments to show that this converges. Of all of the tests, in some sense, the best one to use is the comparison test. If you can compare it to something that converges favorably, you win. If you can compare it to something that diverges favorably, you win. The problem is this is like the method of divine inspiration. You need to know what to compare it to. The easiest ones to use in some sense are ratio and root test. These are extremely straightforward. Calculate the ratio, take the limit. Calculate the nth root, take the limit. That doesn't mean the algebra is pleasant, but there's really no thinking that's needed. The comparison test, you have to think, what do I want to compare this to? Well, if n is large, 1 over n squared minus 1 should be less than, say, 2023 over n squared. Why did I choose 2023? Doesn't matter. I just need some number to be safe to cover my ass. It's 2023 right now, so let's use 2023. For small values of n, I have to worry a little bit. So if I just put in something like that, I should be fine. If I take n to be really, really large, 1.5 would be enough. 1.05 would be enough. 1.005 would be enough. But just take something like 2023 because I don't care. I just want to know that it converges. So I just want to dominate it by something that converges. So, that's, a little bit of analysis that we need. So to determine if something converges, it's just going to do a calculation like that. Okay. What I want to do now is talk a little bit about Lagrange interpolation. So there are a lot of things that might seem impressive initially, and then the more you think about it, it's not that impressive. So I have many skills. One of them is if you give me 2 points, I can actually construct a curve that goes through them perfectly. I can even do this if you give me 3 points. I can do this if you give me 2023 points. I can construct a polynomial that goes through those 2023 points. What's true about that polynomial? Yes, it's almost surely going to be over 2022. If I told you, no matter what you give me, I can do it with a polynomial degree 5, that would be amazing. That no matter what, you're always giving me something with this kind of quintic relationship, it's phenomenal. Yeah, no way that's going to happen. So if I give myself enough freedom, I should be able to get a great fit. What's impressive is if you give me a theory that has very few parameters and you can describe reality with very few parameters, then you've probably sniffed something out. But if you have 25 data points and you have a formula with 28 variables and you can predict those 25 data points precisely, I'm not impressed, right? If I give you a bunch of points to come up with a polynomial that goes through them. So we have, say, points, P1, P2, dot, 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 Pn, with, say, Pk will be the point xk, yk. And let's say all x's will be distinct. Right? How many of you done the method of least squares or regression lines? So if you want to figure out what is the dependence of the angle of an inclined plane and how long it takes the ball to roll down, and you gather all your data at the same angle, do you expect to be able to sniff out how the time depends on the angle? No, right? You've got to make sure you keep changing. So we're getting one data point at each time. So what we do is we form some special polynomials. So let's define fk to be x minus x1 dot 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 x minus xk minus 1 x minus xk plus 1 dot 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 x minus xn. Okay, what can you tell me about this polynomial? Okay, where is it 0? I'm sorry? Not all, except for xk. So sometimes you might want better notation. You might want to write this as the product of all the x minus xk, xl's with L not equal to k. And now I'm going to divide it by xk minus x1 dot 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 xk minus xk minus 1 xk minus xk plus 1 dot 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 xk minus xn. And again, I could write this more concisely as the product L goes from 1 to n, L does not equal to k, x minus xl over xk minus xl. So this is a nice function. We know it has a lot of zeros. So we know fk of xl equals 0 if L does not equal to k. And what does it equal if L equals k? So if I've done it properly, and if I'd actually cared, I would have prepared the lecture ahead of time, but have not. But it should just be 1, right? It's like an indicator function. So this is equal to 1 if k equals L and 0 otherwise. So now let's consider the function, say, maybe some kind of like script f of x is going to be a sum. K goes from 1 to n of fk of x. I'm sorry, times f of xk. So what is f of xk going to equal for any k? It's going to be yk. So here I guess we'll be saying yk is f of xk. So maybe over here, instead of doing this, I should just put in a yk. So here's a way to come up with a function that takes on prescribed values at prescribed points. As long as my points x1 through xn are distinct, this is fine. If they're not distinct, I'll leave that for you as to what would you do in that situation. Yes?
But this isn't a polynomial.
Why is this not a polynomial? It's a polynomial. Each fk of x is a polynomial. It's a polynomial of degree n minus 1.
Because xk is a constant.
Xk is a constant, right? I've just chosen things so that I have these beautiful indicator functions. And by putting them together, I can get a function that takes on prescribed values at prescribed points. So you give me n values, and I can come up with a polynomial that takes on those values. If I want my function to vanish at those n points, can I do that? Well, if I give you the endpoints I want the function to be 0 at, this is not the way to do it. Because if all the yks are 0, what would you get for your function? The function that's identically 0. It works. It's not that impressive. Can you give me a function that vanishes at these points? Yes. Okay, your function's identically 0. That's wonderful. But that also vanishes at other points. Can you give me a function that doesn't vanish at other points? Yeah, just look at x minus x1 times x minus x2 times x minus x3. The question is, what happens in the limit? So for finite values, this is easy to do. If you want to have prescribed zeros, we could look at the product k goes from 1 to n of x minus xk. And that would give me a function that is equal to 0 precisely at the xk's and nowhere else. But as I take more and more terms, I have no idea if this is going to converge, right? Similarly over here, if I take more and more places where I want the function to be known, this is not going to work. There's a whole industry in constructing functions like this. There's been a lot of great work recently on sphere packing, and it involves trying to find functions with certain properties like this, where sometimes rather than the knowing values of a function, you might know values of the function at half as many points as you want, but also values of the derivatives, maybe the first derivative, and then you put all that together. So these are great ways to start, but we have issues with the limits. Issues as n goes to infinity. So my goal is I want to come up with a function with a prescribed set of zeros. And unfortunately, I'd love to just start off by doing something like this, but this isn't necessarily going to converge. I'd love to give a function that takes on a bunch of prescribed values. Again, I have my accumulation theorem and complex. Maybe if I have prescribed values and I have another candidate, I take their difference. They're going to then vanish at those points. Maybe that gives me that the functions must be the same. All right. So we talked about this beautiful function, ek of z, last time. And we showed that if the input z is less than 1/2, as k gets larger and larger and larger, ek of z gets closer and closer and closer to 1. So 1 minus ek of z is, c is a universal constant. Since z is less than 1/2, this is going to be very small. So the moral is ek of z is approximately 1 if z is, if k is small, if k is large. Okay. Why do I want ek to be close to 1? Well, if I now take a product of a bunch of ek's, there's a hope of this converging, right? If I want a product to converge, which of the terms of the product be getting closer and closer to? They should be getting closer and closer to 1. Okay, so the ek's are close to 1. So you should be thinking, let me take a product. All right. I just realized I probably have I brought my Rubik's Cubes down to this class yet? Did I show you the one that's 2 by 3 on some sides? All right, I'll bring that in future. So much of math is about finding the right way to look at something. So does everyone agree that if I give you z minus zk, this has a 0 at zk? This is essentially who's awake right now, okay? Yeah. You should be, yes, I see that if I take z to be zk, this is going to, there's a lot of ways I could write this. I could write zk minus z. Yes? Or I could write it as 1 minus z over zk. Can I do that? Thank you. If zk is not 0. We are not physicists. We will not just divide by 0 or divide by anything without first checking to make sure it's not 0. So there's a little bit of an issue. So maybe a 0 at 0 has to be handled in a special way, but other zeros are fine. And so maybe we could consider a product, k goes from 1 to infinity, of 1 minus z over zk, and I'll put maybe z to the n outside. So these are the zeros at 0, and these are the non-zero zeros, the zeros not at 0. If I have a complex function, let's say my function is holomorphic, what can you tell me about its zeros? If I want the function to be interesting, they can't accumulate. Because if the zeros accumulate, then the function is constant. And in fact, if I have zeros and the function is constant, then the function is the zero function. I'm not going to gain that much by studying the zero function. So my zeros have to go off to infinity. So if f is holomorphic and not constant, zeros go off to infinity. So the hope is maybe this product converges. Maybe for some z, it converges. The problem is, what if the zk's go off to infinity very slowly? Maybe this product could be bad. Does this product look at all like anything related to the e's? Does this look at all like anything related to the e's? Which e is this? Yeah, this is just E0. It's E0, but not at z over zk. So the idea is, this is E0 of z over zk. I take the product over all of them. This will have zeros precisely where I want it to if everything converges nicely. So if my zk's are going to 0, is going to infinity rapidly in absolute value, let's say zk is k factorial, that's really cranking it up, then this product will converge for all z. And the individual terms are going to get extremely close to 1 as k grows. So this function should converge and become a nice holomorphic function. The problem is if the zk's are not growing fast enough. Well, this is the set of data that I have. I can't just say I wish you grew faster. I can, but it's not going to change my data. So rather than using E0, what could I use? EK. And what's nice is EK only has a 0 at z equals 1. So note EK of z over zk is 0 only at z equals zk. Because you have an exponential, the exponential is never 0, and then you have a 1 minus z. So when I put in z equals z over zk, it's only going to be 0 when z equals zk. So what I'm trying to do is I'm trying to motivate the Weierstrass theorem as to where did this come from. It came from, we wanted to construct a function with a prescribed set of zeros. You start off by doing the simplest thing you can. and you see if you can get away with it. If you can't get away with it, what do? You then try to put in some fudge factors. And the fudge factors here are these exponentials. So if I give you if I give you two functions that have the same set of zeros, the functions unfortunately don't have to be the same. Knowing the set of zeros is not enough to uniquely determine the function. This is a common theme. We gave examples earlier where I have a function whose Taylor series has every term 0. Such functions should not be allowed to exist, right? Complex analysis does not allow such functions to exist. They are not holomorphic functions. So if we study differentiable functions, we will not run into them. If you do real analysis, we will run into them. This is why real analysis is hard. This is why probability is hard. We will see later in the semester, I will give you two probability densities that are distinct. So they will assign different probabilities to different events, but they have the same sequence of moments. So knowing the moments is not enough to determine, just like knowing the Taylor series is not enough to determine. So I am never going to be able to come up with a unique function. I will be able to come up with a function that vanishes at the prescribed set and no other place, and any other function will differ from this by the exponential of a holomorphic function, by an e to the g of z. And if you look at this, you can say, oh, yeah, okay, we've got 1 minus z times an exponential of some crap. And instead of using ek z over zk, I could use e2k z over zk. I could use ek factorial z over zk. I have infinitely many choices I can use. And the idea is choose a sequence of k's, choose a sequence of e's such that the product will converge. If my z's are growing very rapidly, just use e0 every single time. If they're growing, but not too rapidly, maybe I could get away with using e1 every time. This is where the book talks about the order of a function. So if your function has a certain order, you have some idea of how quickly the zeros are growing. You can actually then specify this where all the e's have maybe a value of 1 or 2 for their index. But Weierstrass, I love that theorem. I'll say the Weierstrass theorem, then I'll circle back to the previous slide. So Weierstrass says the following: look, let's just get something that works. Let's not worry about getting the best thing that works. So you've got some number of zeros at the origin, fine, that's your z to the m. And then you want zeros at the sequence an, let's look at en of z over an. And then no matter what's going on, we know this is going to converge. And the idea is the following. So proof sketch. So the absolute value of an goes to infinity. So eventually, z over an is going to be less than or equal to 1/2. Because if the ans did not go to infinity in absolute value, what would be true? I'm sorry? What would happen? It would accumulate. If an doesn't go to infinity, you get accumulation. Right? This is one of my favorite theorems. It's completely different than real analysis. If I have a sequence of zeros and they accumulate, then the function has to be identically 0. And it's not that hard to write down a nice closed form expression for the function that's identically 0. So I know my ans have to be going to infinity, so eventually z minus an has to be at most 1/2. And now we can use the result that was stated earlier. So hopefully this will work. Nope. All right. That 1 minus ek of z is at most some constant, some universal constant, times z to the k plus 1. And so now, when we look at what's going on, the EKs are going to be extremely close to 1. So this is telling us that so note En of z is equal to 1 plus something at most, constant times, this is z over an. Z over an, I think it goes to the n plus first power or something like that. So call this whole thing here alpha n. So the product of en z over an is the product of 1 plus an. And this converges if and only if the sum of the an converges. But the sum of an is a geometric series with the absolute value of r less than 1, so it converges. Okay. I'll make sure everybody follows the high-level proof sketch. We know the ENs are close to 1. Well, if they're close to 1, write them as 1 plus a correction. And we know that correction is at most, some constant. Yes?
Sorry, I just can't tell what the last one says.
So the sum of the AN is a geometric series. Try to do it. Is a geometric with ratio less than 1. And so if it's a geometric series with ratio less than 1, it has to converge. So again, we go from trying to understand an infinite product to understanding an associated infinite sum. What is our go-to infinite sum? Geometric series. We love the geometric series. If the ratio is less than 1, it converges. If it's greater than 1, it diverges. And so because the ANs are growing and Z is fixed, for a fixed Z, Z over AN is eventually less than a half. And because my index is growing, I win. This is extremely expensive, right? This is probably nowhere close to what you need to do typically. Can anybody give me a guaranteed overkill way to get rid of a let's say a fly in this room? You might get into trouble for suggesting this. Good, and how would you do that? Atomic bomb, right? Actually, atomic bombs, let's be damn sure we get this, right? So we're gonna have 5 atomic bombs, one after the other, go off in this area. The first one will actually be planted in here. The other 4 will be dropped, once an hour for the next couple of hours. Will we get the bug? Yes, and we'll get a lot more. But we will get, so if all we care about is getting the bug, it's mission accomplished. If we care about getting the bug as cheaply as possible, minimizing collateral damage, not a good job. We're not trying to do that right now. We're just trying to say, here is a function that vanishes at the prescribed set of zeros. Then the next is, what's the cleanest one we can do? And then, of course, the other thing that might happen is I might actually have a function that I care about. Can I factor the function? So we've already done Taylor series for sine. Can you give me a product formula for the sine? Can you write sine as an infinite product? What about the exponential function? Do you think you can write the exponential function as an infinite product? E to the z, do you think you can write that as an infinite product? So what are the zeros of e to the z? There are none. So I can write it as an infinite product up to the exponential of a holomorphic function. Gee, I wonder what the exponential function e to the z, I'll write it as a product of, I guess it'd just be 1 times the exponential of a holomorphic function. Anybody want to guess what that holomorphic function is? Z, right? It's not really, that product is not going to really tell me anything interesting for e to the z, but for sine, yes, that will tell me some stuff. And we'll see that when we get to the Riemann zeta function, we do number theory. I will show you the worst result I've ever proved in my life. If you truly work hard, you will still not be able to get a worse result than I've done. So, you will be able to feel better that you'll never prove a result as weak as your professor did. I at least noticed how bad it was immediately and did not try to publish the original really, really bad result, but I will show that. I will also later give my proof of the Riemann hypothesis, which has one small mistake, but other than that, it's accurate. All right. There was a slide that I quickly went through that I want to circle back to. I'm going to risk asking if people remember things from linear algebra, elementary matrices. You might have seen this in using Gaussian elimination, where you multiply one row by a constant and subtract that from another row and combine things, and you manipulate. Oh, I'm seeing some grimaces. Okay, good. Yes. All right. So these memories are still there, buried, but they're there. And the whole idea is I have a bunch of elementary objects that I understand, and then I combine them. And I combine them in certain orders to move my object from what I have to something that's easy to analyze. And then I analyze that. That's essentially what we're going to be doing now. We take something that's complicated and we keep applying a sequence of operations to convert it to something nice. We saw that to some extent when we were using these nice functions to write a function that vanished at a certain place. Well, we have these matrices, these E's that give us what's going on at a specific point, and then we combine them all together to get our function. Okay, so we can do stuff like that. This is some idea that you have seen before in linear algebra. You hopefully have seen this in other places as well. We will see this when we start doing conformal maps, which will be happening momentarily. Is I want to try to figure out what does a map do? Well, I often break things up into a bunch of simpler operations and I apply them one at a time. Have you guys seen the change of variable formula and the determinant of the Jacobian? How many people have seen that? How many people just want to raise their hand right now so I feel a little bit better about math education? Thank you. All right. Yeah, there we go. Yes, excellent. So you want to figure out, how do I convert from one coordinate system to another? Dx dy becomes r dr d theta. If I have dx dy dz and I'm going into spherical, it's rho squared sine of phi d rho d theta d phi, or rho squared sine of theta d rho d theta d phi, depending on whether you're a physicist or a mathematician, in terms of which way do you do your coordinate systems, which is theta, which is phi. And if you think about it, theta and phi, these are angles. D theta and d phi do not have length. Rho d theta, that's an arc length. So really, it shouldn't be written as rho squared. It should be written as d rho times rho d theta times rho d phi. Each angle infinitesimal should have a rho attached to it. But then you also have this function sine of phi or sine of theta. And that's coming from the Jacobian. It's coming from, how do I change variables? How do I figure out what volume element in one coordinate system would be in another coordinate system? Okay, that's one way that this is often done, is you take a very complicated transformation and you break it up into a bunch of simpler ones. And I prove the change of variable locally for simpler ones and piece it together somehow. So I'm just trying to show you that the stuff that we're doing is related to things you either have seen or should have seen before. Okay, what we're going to do now is move on to conformal mappings. There's a lot more that we can do about zeros of functions and prescribing things. Again, a huge industry is what is, in some sense, the minimal product you need, the smallest indices you need to really get it. If I give you a function like sine or cosine, I don't want to come up with a product for sine that is identical except for an exponential factor. I want to get the actual sine function. And so how do you figure that out? And there's either a homework problem or an exercise in the book, or just some text in the book where they do sine, I think, by using the cotangent identity sum. So with a little bit of work, you can prove that things are exactly the same. And that becomes a little bit harder. Okay. So I'm not going to go through in detail everything from the introduction to conformal maps. I'm trying to put the more straightforward material for stuff to do before class and leave class to just really talk about the philosophy of how do you get there. It's too easy to be reading a math textbook and being able to follow from line 1 to 2 to 3 to 4, but have no idea how they thought to do this. And that's why I wanted to take some time today and try to motivate, where did this product of these E's come from? Well, the simplest thing I can do is, how can I come up with a function, a nice polynomial that takes on prescribed values, or a nice product that takes on prescribed zeros? We talked about that. We then said, well, unfortunately, if we go to the infinity, to the infinitude, we don't know if things are going to converge. So we have to put in convergence factors. And that's where these E functions became useful. And if we just took high enough indices, we know everything is going to converge. right? So we talked a little bit about in the video about inverse functions. F of g of z is z, or g of f of z is z. So if two functions are related like this, we can often transfer information from one to the other without too much trouble. There's a lot of differences between real and complex. So one of the examples, and this is one of my favorites, is we can use this relation to get formulas, for example, like the derivative of arctangent. What is the tangent of arctangent of x? It's x. Arctangent of x is the angle whose tangent is x. So I take the tangent of the angle whose tangent is x. It's not surprising that the tangent of the angle whose tangent is x. And that's why tangent arctangent of x is x. It's almost an English proof rather than a math proof as to why this is true. And then you can go through, you can draw the triangles. Well, if theta is that angle and I want the tangent to be x, there's infinitely many triangles I can draw that are right. The simplest is the vertical is x, the horizontal is 1, then I get the diagonal. And so because fg of z is z, f prime of g of z times g prime of z is 1, I can now find the derivative of g in terms of the derivative of f. So if I know the derivative of f, I now get the derivative of g. I know the derivative of tangent. What's the derivative of tangent? Secant squared. And if you forget the derivative of tangent, what can you do so that this is not a catastrophe? Sine over cosine and use the quotient rule, right? So if you don't remember that the derivative of tangent is secant squared, just use the quotient rule. And so we're able to calculate the derivative of tangent without too much trouble. And we just go through and we plug everything in. Okay. The next thing is, if we have two open sets U and V, does there exist a holomorphic bijection between them? So does anybody remember what bijection is? Okay, so what's a bijection? One-to-one and onto. So that means two distinct inputs have distinct outputs, and you give me anything in the target space, and I can find something in the input space. Well, this of course tells you that there should be an inverse function. If everything in the output space has something in the input space, if f sends me in one way, well, you give me something in the target space, there's got to be a unique thing in the input space that goes to it. That's going to be my f inverse. So it's clear that if I have a one-to-one onto function, if I have a bijection, I have an inverse function. And then the question is, which properties does the inverse function inherit? If the original function is continuous, is the inverse function continuous? If the original function is differentiable, is the inverse function differentiable? And then the question is, are you always able to find bijections between spaces? So for example, if I give you the unit disk, the open interior of the unit disk and the open interior of a unit square, is there a bijection between them? Then is there a good bijection between them? They're both maybe infinite sets, so maybe there's a way to do this, but the function may be wildly non-continuous. It turns out that if I have two sets that are simply connected, I can find a complex holomorphic bijection between them. So not only is there a mapping, not only is it continuous, but it's complex differentiable. And if it's complex differentiable once, what do we know? Infinitely differentiable. And what else do we know? So if the function is holomorphic, it's also analytic. So that it agrees with its Taylor series. That's remarkable. And it turns out in some cases, you can even extend the function to the boundary. Now, it's not surprising that if the regions are different, you might have some issues. So if I have a hole in one region, maybe I don't expect to be able to find a bijection between a space with a donut and a muffin. Yes.
Well, is such bijection like constructive, or do we only notice?
So in many situations, it is just constructive. I'm sorry, it's just existence. In some cases, it is the Schwarz-Christoffel formula. It is actually, for certain polygonal regions, it is constructible. It is the only problem I can remember in my entire college career, this is being recorded, of a math or physics class where I refused to do a homework problem. Is they asked us to extend, this was a graduate mathematical physics class, to explicitly write down the Schwarz-Christoffel formula for one of these. It's like, I'm doing pretty well in the class. This is one homework problem. No. So you can make it explicit in certain situations, but a lot of times it's just something exists with this property. And we want to figure out which spaces are bijective. Because if I have two spaces and I have, say, a nice holomorphic bijection between them, then the idea is if I understand one space, maybe I understand a related space. And I can pass all of my knowledge from one to the other. If you think about this, this is what we did a little bit. I think we talked about ellipses aligned with the coordinate axes and at an angle. Well, if I just change my coordinate system, I can now change the coordinate system so it's now aligned with the axes in the new system. So I can then transfer information from one to the other. And so I study something where it is convenient. This was the big idea in multivariable calculus. Would you rather integrate a nice function over a terrible region or a bad function over a nice region? Typically, we would much rather have the bad function over the nice region. What regions do we like to integrate over? No, we don't. We don't like to integrate over circles. Squares, or more generally, rectangles. So, I mean, a rectangle is just a square with a small amount of discrimination. We can change coordinates again and make any rectangle a square by doing a change of variables, by just rescaling one of the sides. So it is sufficient. If you think about what's going on, what does a circle look like if you were to represent that in polar coordinates? What is the shape in the r theta plane of a circle? Not a line. Well, okay, the boundary would be a line, and so the entire disk would be a square or a rectangle. Similarly, a sphere would just be a box. All we're really doing in multivariable calculus is we're converting nice shapes to rectangles and boxes. And then we know how to integrate over regions like this without too much trouble. So the hope is if I have two different regions and there's a complex holomorphic bijection between them, if I understand one completely, I then understand the other one. And this is where we start having our functions going back and forth. So if I have holomorphic functions from u to u, and I have holomorphic functions from v to v, and I have a nice bijection between them, well, if I want to take a function from u to u, I can associate a function on v to v. I just start off in u. All right, so let's think. I want it to be on v, so I first take f inverse of something in v that puts me in u. I then apply h, and then I apply f, which brings me back to v. So you give me a function h from u to u, and I can associate the function f inverse h f. And conversely, if I give you something, if I want to get something in u and I know something in v, I can first apply f, then apply my function g, and then come backwards. So I really only need to understand one space. And so the search comes down to which is the nicest space to look at. And there's a couple of natural candidates. The entire complex plane, okay? Maybe the upper half plane, maybe a quarter plane or something like that. Or maybe a pizza slice. Or maybe a rectangle of finite width. Or maybe a disk. All of these different things. And there's more than just these, but these are some of the natural candidates. The idea is that if we can understand some of these, we can then pass on to other regions. And so then we talk a little bit about some propositions. The first one, it's a really nice result. If the function is differentiable and injective, then f prime of z is not equal to 0. This is very different than real analysis. I give you the function x cubed equals, my function f of x is x cubed. This is a bijection between -1, 1 and -1, 1, but its derivative is 0 at 0. So once again, things can be different in the complex case than the real case. So I'm going to stop here. We'll do more on this next time in terms of starting to look at conformal maps, but the guiding principle is to reduce things to a simple region. Okay. And then